Okay, so today we're going to go into this topic, okay, which is electronics. And for us, this is a topic that we actually just brushed through, lah, okay, due to the lack of time. So I hope that today's session will be, kind of beneficial, at least for us to know what to focus on and what to know, lah, okay, regarding this topic. All right, let's begin. We have got a lot of questions to do today, and not many of it is repetitive, so we kind of have to go through all this. All right, let's begin with the Kedah question. Diagram 7.1 shows an electron beam that is accelerated from the cathode to the anode in a vacuum space. Okay. Of course, one of the things that you have to remember is that this electron beam is number one, they already given you the fact that it's an electron, okay, but this electron beam is known as a cathode ray. Okay, just so that you know. Okay, potential difference across the electrodes is 500 volts. Okay, so state the type of motion, okay, of the electron beam which moves across the electrodes in vacuum space. So if you remember what is happening, this is thermionic emission. After thermionic emission, they move, and after they get moved, they will accelerate. Okay, so as it goes through this region over here, which is a high voltage region, or we call it the EHT. Okay, the purpose of the EHT is to accelerate the cathode, the electrons. Okay, so the type of motion that we're talking about is either constant acceleration, okay, or increasing velocity. Either one of these, okay, and again, this comes as a set, okay, and why do we know this, okay, it's because of the EHT. Okay, EHT function is to accelerate the electrons. Okay, so increasing velocity, constant acceleration, same meaning. All right. Calculate the maximum velocity of the electron across the cathode and anode. Okay, one very important thing to remember that when we're talking about cathode ray, okay, when we're talking about cathode ray, sorry, brain fart, okay, is that there's only one formula involved, which is half mv squared equals to EV. Okay, but both of these, okay, are formulas for energy. Okay, this one on the left, okay, obviously we know this as kinetic energy, okay, and on the right, okay, this is known as electric potential energy. Okay, the idea behind this is that the electric potential energy happens when thermionic emission happens, and then because of the acceleration, all the electric potential energy will be converted into kinetic energy. Okay, so yeah, sure, you can write it as EV equals to half mv squared. I guess this is better, okay, because EV is electric potential energy that gets converted to become kinetic energy when it accelerates. Okay, so let's put all this in. The charge of an electron is 1.6 times 10 to the power negative 19. V is given as 500 volts, okay, already given just now, all right, equals to half. The mass of an electron is 9.11 times 10 negative 31 times V squared, okay. Don't forget to square root, okay, you will get the answer V equals to 1325259.24 meters per second. Sure, you can do it as 1.325 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 times 10 to the power of 7, okay, meters per second squared. Okay, as long as if you're going to do this, okay, if you're going to put it into standard form, make sure you have at least 3 decimal places. Okay, if you want to write the entire answer according to the calculator, 1325259.1.24, also fine, not a problem. Okay, definitely minimum 2 decimal places, most important. Okay, but as a beginning, okay, and we're going to see this quite often in this particular class, okay, is that when you talk about thermionic emission, one of the most important calculations happens here, which is involving this formula. Okay, and in this case, they're asking you for the maximum velocity, but it needs the whole formula. I think there's another question later that they will ask only the kinetic energy or only the electric potential energy. Okay, so you need to know how these two are related. All right, diagram 7.2 shows the production of cathode rays in a vacuum tube. Okay, shown over here. All right, table characteristics of the heating filament P, Q, and R. You got two choices: type of material and shape. Okay, so based on the suitable characteristics, based on the table, state the suitable characteristics, etc., etc. So type of material, tungsten, copper, aluminium. Definitely, what we can rule out is aluminium lah. Okay, ini memang tidak termasuk pun dalam perbincangan. Okay, so the idea is tungsten and copper, and we know that the biggest difference in tungsten and copper is its resistance. Okay, so that's why I keep telling you all, memorize the metals or memorize the wires with high resistance and memorize the wires with low resistance. In this case, we want tungsten. Okay, because thermionic emission happens because of the resistance. Okay, resistance produces heat that gives the energy to the electrons in order to be able to escape the distance. Okay, so we want tungsten because of its high resistivity. Okay, another one you can also say high melting point now. Okay, but I prefer this answer, high resistivity. Okay, so again, just to remind all of us, the high resistant metals are tungsten and nickel, and then the low resistant metals are copper and constantan. Okay, so remember this as a set, because and of course you need to know when are the situations you need high resistance and when are the situations that you need high current. Okay, next one is shape. There are only two types of shape, either choice A or choice B. Okay, this is coil and this is a straight wire. Okay, in case you don't know how, you can't really draw it out, okay, you have to mention. So the one that goes around like that is called coil, okay, and then the other one is called straight wire. In this case, of course, we want a coiled wire. Okay, and the reason for this is the same, high resistance, because the wire is longer. The longer the wire, then the bigger the resistance. Okay, or more thermionic emission can occur. Okay, more thermionic emission can occur. Okay, so based on the answer in this one, of course, when we look at it, tungsten and coil wire, we want to go for B. Okay, so this is quite an easy answer. All right, let's move on. Perlis, okay, Perlis 2023. Diagram 4 shows a semiconductor diode which is performed by combining type P and type N semiconductor. This is a very interesting question. What is the meaning of a type P semiconductor? Okay, usually it's what is a semiconductor, what is a diode, okay, but interestingly okay, so a type P semiconductor, okay, is a semiconductor with holes as majority charge carriers. Okay, and actually the only difference between the type P and the type N is the word hole. And if you are saying type N, okay, if you're going to say type N, then this word will become electrons. Okay, electrons. You know what? Let me write this better. Okay, so type P semiconductor is a semiconductor with holes, okay, as majority charge carriers. Manakala type N semiconductor is a semiconductor with electrons as majority charge carriers. Okay, the word holes is not what we think of as, you know, lubang-lubang. It's not lubang. In Malay also, the word holes is lohong. Okay, it's a slightly different thing. It's not it's not an electrical component that has holes in it. Okay, it's not. Okay, it's just that these particular charge carriers are called holes. Okay, Why is it? Why can't we call it proton since it is positively charged? Well, that's a good question for yeah, that's a that's a good question now. Okay, the reason why there are holes is because it is not filled by electrons. Okay, so technically, yeah, it's not really positively charged, although in our understanding of it, we look at it as positively charged. Okay, it's just all these slots. Okay, yeah, I think a better word may be slots. Okay, slots that are supposed to be filled with electrons, but if there's less electrons than slots, than empty slots, okay, that means that's a type P semiconductor. More lubang lah, okay, banyak ruang kosong berbanding dengan elektron. But if there's more electrons than empty slots, then we call it a type N semiconductor. Okay, the function of a diode is as a rectifier. Okay, so what is the rectifier? A rectifier is this is a bit strange lah. Okay, biasanya what is the meaning of rectification? So I'm going to change this question lah. I guess what is a rectifier? You can say is a device lah. Okay, a device that converts alternating current to direct current. Okay, if the question asks for what is rectification, okay, just change the word device to a process lah. Okay, rectification is a process of converting alternating current to direct current. Okay, it's a very small difference, I know. Okay, but I think the idea, the main important idea is the conversion of alternating current to direct current. This is the more important one. Okay, if you can get this, then I think you got the entire idea of rectification. Okay, give two types of rectification. So there is a half wave rectification. Sorry, half wave rectification. Okay, and two, this is full wave. Okay, rectification. Okay, the reason why I say that this Perlis question is a little bit interesting is because they allocate 4 marks out of, this is question number 4. Out of 9 marks, 4 marks is allocated for facts. Facts that if you don't know means you don't know, which is a bit strange lah, okay? This is a little bit out of the way. Not very standard lah. I think if they were to ask you facts, they wouldn't make it so like, okay, what is this, what is this, what is this, what is this? It'd be such a torture on students, okay? But since you are revising this, I think it's a good opportunity to learn from this lah. Okay, things that you should remember. I think these are things that you should remember about the semiconductors, okay? All right, so question, this one also is another fact. Okay, a lot of factual questions in this question, so very strange lah. Okay, so the half wave rectification, most important thing is ada current, tiada current, ada current, tiada current. That's all I want to see. Okay, sketch both the output display in the CRO screen for both types. Okay, so this is half wave rectification. Okay, manakala this one is full wave. Okay, full wave rectification is ada current, ada current, ada current, ada current. Okay, most important thing is the difference between the two lah. Okay, so half wave looks ada tiada, ada tiada. Full wave is ada, 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 ada. Okay. As a reminder, okay, half wave rectification uses one diode only. Okay, manakala full wave rectification use 4 diodes. Okay, arranged like this and like this. Okay, the bridge, this one, right? So it's arranged like this, lah. Okay, we'll talk about it in a little while. So the only not so good thing about this question is not only is it lacking marks, number 1. Number 2, is also very factual. Okay, so I'm really not very sure where the Perlis paper is going with this, but in any case, I think it's a good opportunity for us to do a little bit of revision, okay, on this matter. All right, let's move on to the Kelantan paper. Okay, the Kelantan paper is as such. Okay, we're back to term admission. Okay, extra high tension in EHT is used to accelerate the electrons. Okay, but of course, in both cases, the EHT is different lah. One is 1000 and the other one is 3000. Okay, I think everything is written down there. What is the meaning of termining emission? Let's go. Okay, it is the emission, sorry, the emission of electrons from a heated metal surface. Okay, heated metal surface is the keyword over here. Sorry, emission of electrons is the keyword over here. The heated metal surface is the one that, you know, tells you how the electrons are produced lah. Okay, but of course, another thing that you also need to take into consideration is that there is another definition that involves the emission of electrons, which is the photoelectric effect. Okay, this is chapter 7 lah. Okay, I'm doing a lot of going back and forth. Okay, the photoelectric effect has the exact same words, the emission of electrons when a metal surface, oh sorry, you know what, let me put it a little bit better. The emission of electrons from an illuminated, okay, metal surface at a certain frequency. Okay, illuminated means you shine a light on a metal surface, but the light must be at a certain frequency. Okay, but the first few words are the same. Termining emission, photoelectric effect, okay, has the same idea. It's the releasing of the electrons, the emission of electrons. Cuma dia punya kaedah saja berbeza. In termining emission, is a heated metal surface. In a photoelectric effect, it's you know, you shine a light at a certain frequency and then you get the electrons. Okay, the difference, another big difference I should mention over here lah. Okay, I think you have this in your notes. You can just jot this down later. Termining emission process is slow. Okay, photoelectric effect, the process is immediate. But there is a condition. Termining emission got no condition. Asalkan ada haba, boleh sudah. Okay. Photoelectric effect, unfortunately, the frequency has to be bigger than the threshold frequency. Then only you can have the sun. If you shine a light that is less than the threshold frequency, you may not get, you won't get the electrons. Okay, so these are all the subtle differences. The main and important thing is the definition, okay, which I think is the important one. All right, let's compare the power supply. I think if you look at this, power supply in 6.1 is equal to 6.2. The EHT power supply 6.2 is bigger than 6.1. Sorry, let me check. Yeah, 3000 and 1000. Power supply is over here, people. 6 volts, 6 volts. So they're the same power supply. The EHT power supply is different. Okay, so read carefully. 6.2 is bigger than 6.1. And because of that, the velocity 6.2 is bigger also than 6.1. The only thing that you are not shown here is actually the velocity. Okay, but you can kind of infer that if the power supply is bigger, means it will accelerate more. So the velocity will be more. Okay, so using the answers in 6B1, 6B2, relate. First relationship is extra high tension to the velocity. Okay, so let's talk about this. So the bigger the extra high tension, the bigger the velocity. First relationship. Hence, state a characteristic of electron that allows them to be accelerated in the cathode ray tube. No matter what happens, if they ask for a characteristic of electron, the most important characteristic of the electron is that electrons are negatively charged. Okay, very important characteristic across the board. Okay, whenever we talk about how is it that, you know, the electrons can travel here, how is it that electrons can go here, how is it that electrons can go there? Okay, it is because of this important characteristic, is that electrons are negatively charged. That's why we can do a lot of things with electrons, because they're negatively charged. All we have to do is just provide them a positive plate. Then they can do a lot of things. They can go to the positive plate and then do whatever it is that you want them to do. Okay, so very important characteristic. I cannot stress this enough. Okay, that this should be the answer generally lah. Okay, for this. All right, as the electrons move from cathode to anode, what is the energy change that occurs? If you remember from the Kedah paper just now, the energy change that occurs is electric potential energy to kinetic energy. Okay, electric potential energy to kinetic energy. You can use arrow. I don't think it's a big deal. Okay, but just to remind us, electric potential energy formula is EV and kinetic energy is half mv squared. Okay, that's where we get the formula EV equals to half mv squared. Okay, the potential difference of the EHT power supply is increased to 6,000 volts. Okay, calculate the kinetic energy. Calculate the kinetic energy of the electron. I think it's very interesting, okay, that they don't give you anything else. Okay, and they ask you to, oh, okay, 1/2. If you want to calculate kinetic energy, then you use 1/2 mv squared lah. But the problem is they don't give you the V. There's nowhere in the question that actually gives you the V. And the idea is that if your voltage is bigger, your V also has to be bigger because the formula is EV equals to half mv squared. So the question is, how are you going to calculate the kinetic energy if you're not given the voltage? Okay, which also, which is why, okay, this question is very important lah. Okay, because it tests us on our understanding of this energy change. Okay, of course you have to assume that there's no energy loss lah. Okay, which doesn't happen in the real world, but fine. Assuming that there's no energy loss, if all the electrical potential energy converts to become kinetic energy, which means to say that if I calculate the electrical potential energy, I have also calculated the kinetic energy already. Because it's the same value. Electrical potential energy equals to the kinetic energy. Okay, so you can write this as the kinetic energy, okay, is equals to the electrical potential energy, which is just E times V. And this makes our calculation 10,000 times easier already. Okay, is 1.6 times 10 to the power negative 19. Okay, as given over here. Okay, and then the V is 6,000 volts. Okay, this will give us 9.6 times 10 negative 16 joules. Okay, so having this understanding that the electrical potential energy fully converts. I know it's not ideal in the real world, but in physics form 5, everything is ideal, okay? So electrical potential energy converts to become kinetic energy. And so if you calculate the electrical potential energy, essentially you've already calculated the total kinetic energy. No need to find the V. No need to find the velocity. Okay, and that's where usually I think the headache happens lah. Because when we are stuck at, oh, kinetic energy half mv squared. Okay, I can dig out the m from somewhere lah, mass of electron. Ada itu dalam soalan sebelum ni. But where do I find the V? How am I going to calculate the V? And then that's how the 2-mark question suddenly become a 5-mark answer. Okay, super complicated. And by some divine miracle, you get the V. Okay, card lah. Okay, understand this. Energy change means that if you already calculated one energy, you've calculated all the energies, assuming that it is a perfect transfer. Okay, 100% efficiency. All right, let's move on. Let's go to Melaka. Sorry, I'm kind of rushing this, not because of this one, but because there are a lot of questions. Okay, so I kind of don't want to waste time by babbling too much. In any case, I will give a soft copy okay, of this, but I don't actually recommend you looking at the soft copy. The soft copy is actually worse than okay, worse than having this. All right, let's go to what I think is going to be the main essay question now. Okay, if electronics comes out as an essay question, I think that it will be on the transistor. Okay, so far the questions that we've been looking at are all structured questions. This is our first essay question. And I think that a majority of the essay questions, if electronics comes out this year, will be on the transistor. And this is my main focus for today. Diagram 10.1 shows the circuit used as a current amplifier. Okay, name the type of transistor. The downwards arrow tells you that it's an NPN transistor. Okay, if it is an upwards transistor, this is a PNP transistor. Okay, but having said that, I think that especially at our level, at SPM level, most of our discussions center on NPN transistor. Very, very rare actually. I've seen a question on PNP transistor. Okay, but just to be sure, make sure you double check that the arrow is pointing downwards. Okay, if the arrow is pointing downwards, then you know that it's an NPN transistor. Okay, when the switch is closed, bulb X and bulb Y is different. Okay, explain the brightness of bulb X and bulb Y is different. Explain how the situation occurs. One very big indicator for us here is the ampere, the current that is flowing in the circuit. Okay, in this circuit which involves X, okay, this circuit is known as the base circuit. Okay, and this circuit is known as the collector circuit. Therefore, the current is known as a base current and the collector circuit current is known as a collector current. Okay, notice that the value of the base current is in microamperes, which is times 10 to the power negative 6. Manakala in collector circuit is milliampere is times 10 to the power negative 3. It's a 1,000 times difference. Okay, it's a 1,000 times difference. Okay, 3 zeros at the back. So obviously the brightness is going to be different. So how do we answer this question? 2 marks you allocate for the condition of the bulbs. Okay, if you take a look, bulb X will be less bright because there's less current flowing. Okay, so bulb X is dim, 1 mark. The second one is bulb Y is bright, brighter lah. Okay, brighter than X. Okay, or any other variation of it lah. Okay, you can say bulb Y is dimmer, bulb X is dimmer than Y. Okay, bulb Y is bright. Either one is fine. Then, sorry, I don't know if you can hear that sound. Oh, okay. There's a guy blowing leaf. There's a leaf blower outside my place lah. So yeah, anyway, so this is 1 mark. This is 1 mark. So then after that, you need to explain why is it that bulb X is dim and why is it that bulb Y is uh bright. Okay, I think the simplest explanation for bulb X is dim, okay, is that the base current, okay, is low. Okay, then you can put lah in microamperes. Okay, just to show that wow, it's so low because it's times 10 to the power negative 6. Okay. Another way to explain this, okay, is that there is a resistor over here. Okay, so the presence of resistance or presence of a resistor lah, okay, limits the base current. Okay, when there's a resistor, then you know there's a limit lah. Okay, the high resistor value, okay, will limit the base current. So the base current is actually very low in the amperes. Okay, the second explanation, okay, is about bulb Y. So you can flip it the other way lah. Okay, the collector current, okay, is high, at least higher lah. Okay, in milliamperes. Okay, and the reason why the collector current is high, okay, is because the transistor amplifies the current. Okay, and results in a big collector current. Okay, so I think this explanation is very important lah. Okay, and you cannot run away. Whenever you talk about transistor kan, memang base current sangat kecil, collector current sangat besar. But the interesting thing is, if you remember our thought of our pattern of thought, our train of thought lah. Okay, is that in order for collector current to flow, there must be base current. There must be enough base current flowing. Although it's very small, okay, but there must be base current flowing. If base current flows, then transistor switches on, then after that, the collector current flows. But having the small base current, which produces a big collector current, is the thing that the transistor is made for, okay, as a current amplifier. Okay, kamu bekalkan satu arus yang kecil, terus kau dapat satu arus yang sangat besar. Wow. Okay, it's the best of both worlds. It's that you put in a little bit of effort, then you get 100 marks for SPM. Wow. Okay, so these are the explanations for this lab. So either one of these is 1 mark, and then after that, this is also 1 mark. Okay, I would actually recommend you, if you're going to be memorizing this answer, I would actually recommend you to memorize the second line. I think the second line is a better explanation. Okay, the fact that the presence of the resistor limits the base current. It sounds more distant. I fear, okay, yang saya takut adalah yang baris pertama ini kan, dia kasih sama dengan ini. I'm afraid that this might happen. They say, oh, bulb X is dim or base current is low. Same mark. Okay, so you don't want to be repeating that. The second line, the presence of the resistor limits the base current. I think this is definitely a better chance for the second mark now for the explanation. All right. So we have a transistor circuit over here, and then you're given these choices, W, X, Y, Z. Using your knowledge of electronics, choose any 4 appropriate electronic components to complete the transistorized circuit. Oh, wow. This is the first time I've seen this word. But anyway, let's go back to the question first. Hold on. Oh, okay. Mrs. Sheila needs to monitor her baby who sleeps in another room. She needs a trigger in her room to alert the baby if the baby wakes up and starts crying at night. Oh, okay. So she wants to hear the baby, and then she wants to have something tell her that, oh, okay, baby is awake or something like that. Okay. So what we need obviously is an alarm. Kan? A trigger lah. And a microphone, because babies will cry. Yeah, babies will cry lah. So these are the these are the memang essentials that you must have a microphone and you must have an alarm. And just by doing this, you can see that we're going towards Y already. So we need a rheostat, we need a capacitor. Okay? Because of the fact that we must have the microphone, we must have the alarm, and this is the only one that has it together. Okay, so actually this question becomes quite simple. Rheostat, capacitor, microphone, and alarm. So of course, the reason, okay, so the reason for rheostat, okay, the reason for rheostat, hold on, the reason for rheostat, it can have changing resistance in order to switch on the transistor. Okay, it needs to have a changing resistance because you don't know how loud the baby is going to the baby is going to cry. Yeah, you don't know how loud the baby is going to cry. Okay, let me say we put the rheostat over here. Okay, we put the rheostat over here in P, and then we put the capacitor in Q. So here is the capacitor, and then R is the microphone. Gosh, microphone. Oh no, I think salah. Sorry. Should be like that. Yeah. Okay, this is a microphone, and then S will be the alarm. Okay, S will be the alarm, so it will be like that. Okay. So S will be the alarm. This is the mic. This is the alarm. Okay. So what happens is that the mic picks up the sound. Okay. And when mic picks up the sound, okay, it becomes alternating current lah. Okay. So the capacitor, wait, hold on now. Oh, okay, fine. So what the capacitor does is the capacitor stores the charge. Okay, it stores the energy lah. Okay, and then what happens after that is because the mic is picking up, different sounds. Okay, so there'll be different resistors coming through. So the function of this changing resistor is to change the resistor so that it can absorb enough. It can absorb some lah. Okay, some of the not absorb so that some of the voltage can go onto the top part so that enough voltage will be at the base circuit. Enough voltage base circuit and blah 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 blah, blah okay, that train of thought. Okay, but for now, let's just set it as the rheostats function is to change the resistance, so that the transistor can be switched on. Capacitor actually can't really run very far. Interestingly, there's really no choice for Q. Everything also must be capacitor. Okay. The current flow in the capacitor is in the base circuit. Can, why not? Its job is to store charge, not to stop charge from flowing. Okay. I think the best explanation, this one I have to refer to the black book for this is to stabilize Okay, is to stabilize the flow of current in the base circuit. Okay. Because when the current flows, as I said just now, when the baby cries, it doesn't cry at a steady current. No there'll be loud, soft, loud, soft, loud, soft. So when the microphone picks up, the loud, soft sounds, will give different currents at the same time. And that's going to spoil the transistor. Because sekejap ada current, sekejap currentnya tinggi, sekejap currentnya rendah. That's not very good. So the function of the capacitor is to store the charge and to make sure that the current flow is a lot more steady. Okay, actually, the best idea in order to think about this, think of the rectifier circuit lah. Okay, the function of the capacitor is to smoothen the current. Okay, this is going to get a bit technical. Sorry. So if you remember full wave rectification, without capacitor, the graph is like this. With capacitor, it becomes a lot more stable. Okay, so we want the current to be a lot more stable in order to protect the transistor. Okay, so that's why I said I think the better reason for the function of the capacitor is to stabilize the flow of current. Okay, not to let the current flow one way, but to stabilize it lah. Okay, because the baby sound is going to be whatever the sound is lah. Okay, and it's going to be very, very inconsistent, and that's going to kill the transistor, because if there's no capacitor there, the transistor is just absorbing all this changing current. Dia sendiri pun akan jadi marah. So the function of the capacitor is to stabilize the flow of current by storing the charge, so that it only allows a certain amount of current to flow through. And when the current is stable, then your transistor can switch on with ease. Okay. The rheostat is to change the resistance. Okay. Microphone, I think the easiest function of the microphone. Oh dear, I don't have space to write this. Okay, microphone. You know what? I'm going to write this over here. The function of the microphone is to convert sound energy to electrical energy. Okay, this is a physics answer. I know the function of the microphone is to pick up the baby sounds, but wow, where's the physics in that? Okay, so to convert the sound energy to electrical energy, or signal, sound signal to electrical signal. Okay, and finally, to the alarm is to convert, this is so terrible, electrical energy to sound energy. Okay. Or, yeah, lah, I know the function of the alarm is actually to, to ring when the collector current flows, lah. I think, okay, fine. To, to produce, okay, to produce sound when collector current flows. And this also is a possible answer, lah. Okay, the function of the mic is to convert the sound to electrical. Function of the alarm is to produce sound by having the electrical energy, so from electrical to sound. Or in other ways, when the collector current flows, then it will ring, lah. Okay, so that's the idea behind this question. This is a good question, actually. What state is this? Melaka. Very good question. Okay, a little bit simple, lah, I find, because, like, for example, Q, you got no other choice. No? So more capacitor. Okay, so it's like, okay, so there's no other choice in Q, lah. It must be capacitor. Okay, that's this one. It's quite simple, but I think maybe where students will struggle with this question is the explanation, lah. Okay, how to explain this, especially the capacitor part. Okay, remember that the function of the capacitor is to stabilize, to smoothen the current flow, so that it doesn't go wah 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 like that. Rosak kamu punya peranti. Okay, kalau begini berlaku. Let's move on. This is the calculation question. Okay, resistor R is a variable resistor. Okay, while resistor N has a fixed resistance of 500. Okay, transistor can be turned on when the potential difference across YZ is equal or higher than 1 volt. Okay, let's say minimum lah, 1 volt. Okay, determine the potential difference across XZ. Okay, so when the potential difference is 1 volt. So you already say here 1 volt. Now if you remember, the whole thing here is 3 volts. Okay, sama dengan yang dibekalkan. So if they've already given us YZ is 1 volt, so logically, okay, XY will be 2 volts. No need to think about this. Okay, it's a very, there's really nothing to calculate, it's just logic. Okay, but question is across XZ, daripada X sampai ke Z. So the answer for this is 3 volts. This is only a 1 mark answer, lah. Okay, there's a mistake in this question. This is 1 mark and this is 3 marks. Please correct this. Question number 2 is only 1 mark. Also, the potential difference across XY is 2 volts. Okay, from the logic that we determined just now, lah. Okay, across XY, okay, this part over here, okay, is 2 volts, because if YZ is 1 volt, means the voltage in XY must be 2 volts. Okay, so the maximum resistance R so that the bulb T lights up. Okay, so essentially they are asking, okay, kalau sini is 1 volt and this is 500 and this is 2 volts. So how much should this resistance be? Okay, look at it logically. Kalau 1 volt is 500 ohms kan, 2 volts. Okay, there's really nothing to count, I feel like it's free 3 marks. Okay, 1000 ohms lah. Because kalau 1 volt, kamu perlukan, if you want 500 ohms to have 1 volt, you need 1000 ohms to have 2 volts. Because the bigger the resistance, the bigger the voltage. Okay, that relationship very important. And remember transistor, we always talk about this. Big resistance means big voltage means big current, blah, 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 blah. Okay, so I guess if you really want to show, because this is a 3 mark question lah, okay, you can actually I also don't know, because I've always been doing it like, pakai logic said 1 volt is 500, so 2 volts is 1000 lah, like oh wow. Okay, I guess if you want lah, okay, you can use the potential divider circuit. 2 volts equals to R, what is this one? RR. Okay, the resistance of R over the total resistance times 3. Okay, because you have 2 volts equals to that particular, remember this relationship? Oh, actually, you know what? Let me write it this way. 2 volts out of the 3 volts equals to the resistance of R over the total resistance. Okay, or if you want to use the logic from just now, 2/1 equals to RR over 1 over 500. Also can. Yang kita pakai tadi lah. Okay, if 1 is 500, 2 is how much? Okay, so you RR equals to 1000 ohms. Okay, either one also can lah. I feel that this is a very easy 3 marks, and I really don't know why there's so many marks for a very simple calculation. Okay, if you're going to use this, so it'll be 2/3 equals to RR over RR plus 500, because the total resistance is these two added together, the resistance of R plus 500. Okay, so this will, when you calculate this, you will still get RR equals to 1000 ohms. Okay, there's really no way going about this, because it's a what we call a ratio formula. Okay, it's a potential divider circuit formula. Either way you can do it. I feel that even if you write the answer just alone by itself, or if you write these two lines, 1 volt equals to 500, therefore 2 volts equals to 1000. You should be able to get the mark. Okay, but I think that this question is easy enough for us to understand lah. Like, it's logic saja apa itu. Kalau 1 volt kan dia 500, 2 volt must be 1000 lah, because that proportion is there. Okay, that in the directly proportional thing is there. So I don't think you should overthink this lah, especially if you're the kind of person that doesn't like complicated calculation questions. Bagus kamu tulis saja jawapan dia terus, especially when you understand what is happening. Okay, our next essay question is from Negeri Sembilan. Okay, there are a lot of essay questions lah, which is why we need to rush this. Okay, 11.1, 11.2 shows cathode ray attracted to positive plate when a deflection tube. Okay, so we're back to the cathode ray again lah. Okay, which is thermionic emission and then transistor. Okay, just remember, question 11 is the no choice question. You have to answer the question, but there's a comparison involved, and there's also the design question. Okay, so what is the meaning of thermionic emission? We've covered this in the previous question. Okay, the emission of electrons from a heated metal surface, etc., etc. Let's move on. Compare the extra high tension value. Okay, take a look at the extra high tension, 5000, 3000. So 11.1 is more than 11.2. Okay, the deflection angle of the cathode ray. Okay, take a look. Okay, if you want to look at the deflection angle, what you do is you draw a straight line over here and take a look at this angle, compared to a straight line over here and take a look at this angle. Okay, if you take a look at both angles, you notice that 11.1 is also bigger than 11.2. Okay, draw a straight line and just look at the. I know it's a curve, but just agak the angle lah. You notice that the angle is much bigger in 11.1 compared to 11.2. Okay, so the deflection of the angle of cathode ray 11.1 is bigger than 11.2. The final one is the attraction force of the plate on the cathode ray. Okay, since the EHT is bigger, the attraction force will also be bigger. So 11.1 is bigger than 11.2. So the good news is, for all three comparisons, they are the same direction. 11.1 is bigger than 11.2. So relate the extra high tension and the angle of deflection. So the bigger the extra high tension, the bigger the angle of deflection. I think it's very simple. Okay, and finally, relate the angle of deflection to the attraction force of the plate. The good news is, everything in this one, okay, everything is the same direction. So there's really no way you can mess this up. Okay, the bigger the angle of deflection, the bigger the attraction force, okay, of the plate, which is not right. Okay, because attraction force is the one that causes the angle of deflection. Okay, so this one has to be written terbalik. Okay, the bigger the attraction force, okay, the bigger the angle of deflection. Okay, be very careful lah. Okay, be very careful. I know it's very easy to go automatic mode lah. So, semua besar-besar bah ini. Kan semakin besar semakin besar. It's very simple. But make sure that the relationship makes sense. Mana yang penyebab dan mana yang mempengaruhi dan mana yang bergerak balas. Okay, very, very important. Okay, describe what happens to the cathode rays, okay, when the EHT terminals is reversed. Okay, so in this particular case, let's just take the top one over here. Okay, the top plate is positive, the bottom plate is negative. So the first thing that happens is that the bottom plate becomes positive. Right? Okay, so the bottom plate becomes positive. Okay, and because the bottom plate becomes positive, the cathode rays are drawn or attracted, are attracted to the bottom plate. Question is, explain what happens. Or describe what happens. Oh, okay. Describe what happens. Okay, the bottom plate becomes positive. The cathode rays are attracted to the bottom plate. I guess you have to explain why lah. Okay. The reason is because cathode rays are electrons. Okay. Cathode rays are electrons that are thermionically emitted. It's a very strange word lah. Okay. And because of that, electrons are negatively charged. Okay, the bottom plate becomes positive. The cathode rays are attracted to the bottom plate. And the reason for this is because cathode rays are actually electrons that are thermionically emitted, and electrons are negatively charged. Negatively charged. Okay, and because they're negatively charged, okay lah, and will be attracted to the positive plate. All right, let's continue. So diagram 11.3 shows a mobile phone with a specification of 9 volt and 15 watts. Sorry, this is not right. Mobile phone with a specification of, oh, okay, fine, 9 volt and 15 watts and a battery charger to be used. Okay, fine, 9 volts, 15 watts, battery charger to be used. If it's not clear to you on here, the input over here is 240 volts, okay? That's actually these are the only two things that are important for us lah. Okay, 240 volts and 9 volts. Okay, I will explain why in a little while. But the main idea behind this question, actually this question is a combination of two chapters, electronics and also electromagnetism, because we need to talk about transformers. Okay, but I don't know if I photostated this and this is clear. If it is not clear, write it down lah. Okay, 240 volt and 9 volts. Okay, it becomes very important for us in a little while. Okay, using the appropriate physics concepts, explain how to build a battery charger for a mobile phone based on the specifications required. Okay, your answer should include the following aspects. Okay, if you have the black book, it's on page 70 lah. Okay, the answer is in page 70. Otherwise, let's talk about the answer. Okay, so the input power supply should be an alternating current. Okay, alternating current power supply. Okay, and the reason for this is, remember that anything lah, okay, any electrical outlet in the plug there's a mini transformer that actually transforms or that actually changes the output voltage from 240 volts. In our plug is 240 volts, but not everything in our house uses 240 volts, so it needs to be stepped down even more. And when you talk about step down transformer, you need to talk about electromagnetic induction. Okay, so and when we talk about electromagnetic induction, you must talk about the changing magnetic field. Okay, but either way, if the question is talking about alternating current power supply, which most likely it will be, okay, alternating current power supply, okay, the reason for this is to produce a changing magnetic field. Okay, the biggest reason that you would choose the alternating current power supply, okay, is because it can have a changing magnetic field. And by extension, if this is a electromagnetism question, then you need to know the extension. Okay, changing magnetic field means you can have electromagnetic induction. When electromagnetic induction can occur, then you can step up and step down the voltage. Okay, so this is the train of thought, but that's in another chapter altogether. Okay, but for the purposes of our question, okay, just remember that if it is an AC power supply, alternating current, the reason that you would choose an AC power supply would be to produce a changing magnetic field. Okay, enough for that. Okay, the ratio of the number of turns. So if you remember the transformer formula, the primary coil over the secondary coil equals to the primary voltage over the secondary voltage. Okay, so the ratio has to be the same as the primary voltage over the secondary voltage, which is why in the question just now I said the only two important information that's important is 240 and 9. Okay, so the ratio should be 240 to 9. But let's simplify this. I wonder whether got 200. Oh, sorry, 80 to 3. Okay, 80 to 3 also can. Okay, so the ratio should be 80 to 3 or 240 to 9. And we get this from the primary voltage over the secondary voltage. Okay, and the reason for this is to reduce the output voltage or to step down the output voltage. I don't want to so can lah. Okay, you can reduce the output voltage, step down the output voltage. Okay. Sorry, this is a side note. There are a lot of side notes in this question because ini melibatkan banyak bab sebenarnya. Okay, and I'm taking the opportunity to revise with you. Transformer, okay, transformer, the definition of a transformer is a device that increases or decreases the output voltage. Okay, the key word here is the word output. Okay, this is in recent years we found out that for the definition of transformer, the word output must be there. Kamu bukan sekadar menaikkan dan menurunkan voltan saja, tapi dia adalah voltan output. Okay, increasing or decreasing the output voltage. And the reason why I'm emphasizing this is because the word output must be there. In case the question comes out, make sure that you write the word output. Okay, anyway, let's come back to the question. Okay, electronic components and the number of components for the rectification process. What am I doing? Electric components and the number of components for this one. Okay, so far we have one mark here, one mark here, the second mark, this is the third mark, this is the fourth mark. So I need to have another 6 more marks, which I need to have another 3 more points. Okay, so I think the electronic components, if you're talking about rectification process, there are only 2. The first one, okay, I'm going to diodes. Okay, add additional component. Okay, is diodes. Okay, and the reason for this, diode is always to convert alternating current to direct current. Okay, I wouldn't recommend the answer for rectification because that will be, that will be for the number of diodes okay, which is the 7th point. Okay, sorry, this is the 6th mark. So the 7th mark is to write down there 4 diodes. Okay, because they're asking for the number of this one. Okay, and the reason for 4 diodes is so that full wave rectification can occur. Okay, so this is the 8th mark. Okay, so I would advise against writing rectification in this section. Okay, better to state lah, to convert the alternating current to direct current, which is basically what the diode's main function is. Okay. And then after that, in the 4 diodes part, you talk about the full wave rectification. Okay, the 9th mark would be the other component lah, okay, which is usually the capacitor. Okay, add another additional component, the capacitor. And the standard answer for capacitor, as we've talked about just now, is to smoothen the current. Sorry, output current. Okay, to smoothen the output current so that it's a consistent flow. Okay, so I think after a while, and we may not actually have enough. We may not actually have enough questions that talk about this, but I think it's good that 1 or 2 questions talk about this. After a while, you notice that the pattern of asking about the rectification questions really cannot run far. Okay, so you remember, as I said, diode is for this. 4 diodes is so that you can have this. Capacitor is for this. And if the question comes out in electronics, at least you have, okay, saya ada sudah jawapan begini dalam tangan. Okay, then you just need to memorize this. Okay. Okay, if you want, you can, they also ask for the number of components lah. Okay, so I'm just going to give you an extra one. Okay, I'm going to call this the 11th and the 12th mark, although it doesn't exist lah. Okay, you can have one capacitor. Sorry. Okay, one capacitor. Okay, arranged in parallel to the battery. I think this answer is in the book on page 70. Okay, one capacitor arranged in parallel to the battery. Okay, but the reason for this is the same, to smoothen the output current. Okay, to smoothen the output current. So the only additional thing actually here is to parallel with the battery lah. Okay. All right, let's continue. Oh wow, it's here. Page 70. Yeah. Okay, page 70 is here. The only one that I would advise is this 30 to 1 lah. Okay, 240 to 8 volts. So the ratio of turns in this question, remember that this answer, the 30 to 1 or 240 to 8, really depends on the question. Our question is 240 to 9 or 80 to 3. And where do we get this from? We get this from the question. Okay, take a look at the big voltage and the small voltage. If you want to step down, big voltage first, then stop small voltage at the bottom. If you want to step up, then it's the other way around lah. Okay, small voltage first and then big voltage. That's why I said this information over here is very important. Okay, important for us. Okay, so everything else, I think you can write down. Full wave rectifier to convert, use a capacitor to smoothen the current, steady direct current. Okay, use 4 diodes, full wave rectification, etc., etc. Okay. Right, let's move on to Pahang. Another essay question. I know there's a lot of essay questions this round compared to the previous classes, which should give us a very important indication. Okay, all right. Shows a simple circuit of a fire alarm. Oh yes, one other thing. The good news about this class is everything about transistors is covered in this class. That means we talk about fire alarm, we talk about light, later we talk about light. All the important circuits in transistors are covered. So when you have the handout, you just need to look at the handout lah. Okay, towards the exam, as you get nearer to the exam, look more and more at the handout so that you can memorize the answers. Okay, when there's a fire, buzzer will be activated. Oh wow. Okay, what is the function of the transistor in diagram 10.1? Okay, diagram 10. In this particular diagram, okay, it functions as an automatic switch. Okay, transistor has 2 main functions. Number 1, it functions as an automatic switch. Fire alarm, the baby one just now. Okay, the light automatically come on. All those are automatic switch circuits. The other function of a transistor, okay, the other function of a transistor is a current amplifier. Okay, and how do you know whether the circuit is an automatic switch circuit or a current amplifier circuit? Current amplifier generally lah, okay, generally current amplifier kan dia memerlukan microphone. Okay, it needs a microphone and you talk a bit and you amplify the sound. You want to make the current bigger. Okay, so you want to make something very small become very big. So that's a current amplifier circuit. One of the indicators is not the only indicator. One of the indicators is if you see a microphone, most likely it's a current amplifier circuit. Okay, like in the case of the baby just now, the baby and the microphone, the alarm, right? That's a current amplifier circuit because baby cry very small, then you know the sound become very big because the alarm. If there's a speaker, sorry, microphone and speaker. Astaga. Okay, microphone and speaker. Okay, but when you have a buzzer, when you have an alarm, when you have a light, usually it's an automatic switch lah. Okay, like at night, the lights automatically switch on. Okay, it uses a transistor for that. Okay, this question, sorry, when the switch is closed, but please cut that one out. I don't know what this is doing in the question. This is the question from Kedah just now. Okay, but the question is explain how the buzzer will sound when there is a fire. Okay, I went through this with all of you, well, at least in our class lah. I said that, okay, when you talk about transistor, you must talk about this, and then finally, no. Okay, so you need to think about that thought process. So let me remind you once again, okay, the transistor flow chart, it must be always there. There's always a starting point and there's an ending point. All the explanation regarding transistor, sorry, after the leaf blowing, now there's a grass cutting process going on. I'm not gonna get a break. Okay, anyway, I hope that the grass cutting sound is not distracting. Okay, so in all the transistor circuit explanations, follow the flow chart. The only thing that changes is the starting point and the ending point. Okay, the starting point and ending point is the only thing that changes. In this case, the starting point is thermistor means there's a fire lah. Okay, so in our case over here, the fire, sorry, okay, has low resistance. Okay, in a fire. That's our starting point. Because when there's a fire, it's hot. And when it is hot, the resistance becomes low. So this green over here is very important. LDR, which is a light dependent resistor, at night is high resistance. Thermistor, when it is cold, it is high resistance. So when you talk about fire, okay, the fire, the thermistor resistance becomes low. Okay. And as we have said many times previously, when this is low resistance, this is high resistance. Okay, the base resistance is big. Okay, it's bigger compared to the thermistor resistance. Okay, and follow the flow. When the base resistance is big, the base voltage is high. When the base voltage is high, base current flows. When the base current flows, transistor switch on. When the transistor switch on, collector current flows. Collector current flows. What is our endpoint? Our endpoint is the buzzer. The buzzer rings. Okay, so the only one that changes actually, okay, is our starting point and our ending point. Everything else in between should not change. Okay, which is what makes the transistor circuit very easy to do, because kalau kau tidak cakap pun the starting point and the ending point, right, everything else in the middle is at least 2 marks. You can get the 2 marks. Okay, if you don't know what is the starting point and astaga, takkan ending point. I think ending point saya rasa masih boleh lah. Okay, so have that train of thought in mind. Okay, the most important thing is that the base resistance must be high, must be bigger. When the base resistance is bigger, then the base voltage is high. Base voltage is high, current flows. Current flows, everything is automatic after that. Okay, so I'm putting this guide up for you. Anyway, if you want the proper explanation, it's in page 150, okay, in your black book. Okay, but if not, use this as a guide. Okay, what is the starting point and what is the ending point? Everything in the middle doesn't change. Base resistance high, voltage resistance high. Sorry, base voltage high, base current flows. Base current flows, transistor on, collector current flows, T dot D dot or ching ching, up to you lah, whatever that happens at the end. Okay, so once you have that kind, then you don't have to memorize so much already. Okay, because this explains everything. LDR circuit, thermistor circuit, everything is explained there. All right, let's move on. Okay, based on diagram 10.1, if the potential difference in YZ is 0.5, buzzer will sound. Okay, so dia cakap di sini YZ is 0.5 volts. Okay, now if you remember the question just now, if this is 0.5 volts and the whole thing is 3 volts, sini adalah 2.5 volt. Really nothing to think about. Okay, so the potential difference across XY will be 2.5 volts. Okay, XY lah. All right. The current flow in XZ. Okay, XZ, sorry, 0.5 is 2.5 volt. Okay, X to Z. Okay, current flow. So this is the hard part lah. Okay, remember that in Ohm's law, V equals to IR. Okay, but the problem is, I don't know what is the resistance of the thermistor. Okay, but if you take a look at this, these two, okay, this is actually a series circuit. Okay, and in a series circuit, oh, the grass cutter sound is really very annoying. Okay, in a series circuit, the current is the same in each resistor. Okay, that means if you count the current for the resistor over here, it's the same as the total current because current is the same. Okay, so the current flowing through XZ is essentially, the voltage is 0.5, the current is on, the resistance is 1 kilo ohm. 1 kilo ohm is 1 times 10 to the power of 3. Okay, so the current is 0.0005 amps. Okay, you can write this as a side over here. Okay, in a series circuit, the current in one resistor is the same as in all resistors. So if you calculate the current in one resistor, you already calculated the entire current for the whole thing. Okay, so when you calculate the resistance in one, when you calculate the current in one resistor, you're actually calculating all in a series circuit. Okay, not parallel circuit. Parallel circuit is voltage. Okay, so once you have the current flow, then you can calculate the resistance already. Okay, because we're using the same V equals to IR. We know that the V is 2.5. Okay, from our logic just now lah. Okay, so 2.5 equals current flow is the same, 0.0005, and then you can calculate the R. Okay, and when you do this, you will get R equals to 51234, yeah, ohms. Okay, or 50 kilo ohms now. Hold on, 50,000 ohms. Okay, roughly there. So this, I guess, the reason, maybe a reason why this chapter is a little bit challenging for some is because it draws its questions, although mainly from electronics, some of the questions come from chapter 3, electricity, some of the questions come from electromagnetism. Okay, it's all somehow interconnected lah. Okay, so, but don't worry, okay, if you can just stick to the basics first, make sure your basics are okay, and after that, we can take it further from there. All right, let's move on. 10.2 shows a house on the edge of the forest. Okay, the owner wants to install all spotlights. Okay, when you see spotlight, then you know that this is LDR circuit. The spotlight should be lit at night and turn off by itself during the day. For electronic, this one, okay, you have 4 circuits over there. You are required to determine the most suitable electronic circuit to light up 3 spotlights, okay, with normal brightness. Normal brightness means you must have 240 volts, okay, shining on it. Okay, position of the LDR, connection of the batteries terminal, arrangement of the spotlight circuit, use of a relay switch. Okay, so let's begin. Position of the LDR, okay. So this one has to be remembered lah, but remember that thermistor LDR is opposite. Okay, in our previous question just now, the thermistor was on top. So, you know, the LDR has to be at the bottom. But you can't write the words at the bottom. Okay, that's not the answer. Okay, so the position of the LDR, okay, in this case, we're going to say it's at the base circuit. Okay, this is what it's called. At the base circuit. Connected to the base circuit lah. Okay. Yeah, you know what? I think we should write the words connected to the base circuit better. Okay. So, and the reason for this is high resistance when it is dark causes base current to flow. Okay, main feature of the LDR, as I mentioned just now, is at night the resistance is high. If resistance is high means the base current, the base resistance is high means the base voltage is high means base current flows. I know I'm skipping step 2 and step 3. I'm not going to write the entire thing in my reasoning lah. Okay, the idea is if the base resistance is high where the LDR is, then the base current can flow lah. Okay, so I'm essentially jumping from step 1 to step 4 lah, in this reason. Okay, high resistance when it is dark. This is a very important feature in LDR. Okay, it has high resistance when it is dark so that it can cause the base current to flow. Okay, second one, the connection of the batteries in terminal. Okay, the connection, if you notice over here, there are 2. One is the one is the positive is connected to the collector. Okay, and the other one is the positive is connected to the emitter. Okay, positive connected to the emitter. So the one that we want, okay, is this one. The positive is connected to the collector. Okay, which is how we would write this lah. Okay, positive terminal of battery is connected to the collector. Okay, positive positive is connected to the collector. Okay, and the reason for this, this is simple lah. The reason for this, okay, so that it is a forward bias. You know what? Let's transistor is connected forward bias. Okay, let's continue. The arrangement of the spotlights in the circuit, there's only 2 kinds of arrangement, which is, in this case, is parallel. In this case, is in series. Okay, obviously we want it in parallel. Okay, so the arrangement of the spotlights in circuits should be in parallel. Okay, so that and the reason, the reason for this will be all bulbs can receive 240 volts of voltage supply. Okay, 240 volts of voltage supply. Actually, if they didn't write this one, if they didn't write this normal brightness, you can actually put the answer for normal brightness. All the bulbs will shine with normal brightness. Okay, but the problem is it's already in the question. So you have to change the answer to they will be able to receive a voltage supply of 240 volts so that they can shine with normal brightness. Oh, wow. Okay, which is why the specification is given over here. Okay, very important. All right, the use of a relay switch in the circuit. If you actually take a look, there's only one that doesn't have. Okay, but at this point, you already have three and you are already looking at circuit Y lah. So memang kena ada guna. Okay, so the answer for this would be relay switch is used. Okay, and then the reason for this is to switch on the secondary circuit. Okay, I think in the black book, if I'm not mistaken, in page 68, they actually give you a short explanation about the relay switch lah. Okay, either 68 or 69, I can't remember. But they actually give you the explanation on the relay switch. Like, why is there a need for relay switch? What's the point of the relay switch? At our SPM level it's just kamu perlu tahu saja yang kewujudan relay switch itu. And the reason for the relay switch is because the transistor is a very small and delicate equipment, and the transistor alone cannot light up, the three bulbs. The main function of the transistor is to function as a switch. And when it turns on, when current can flow, then the relay switch can be turned on. When the relay switch can turn on, then it can handle a much bigger voltage. If you notice here, it's 240 volts. Okay, the transistor only functions with 6 volts only, very, 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 very small. So we cannot put all the bulbs on the transistor circuit itself because what is going to happen? 6 volts only, you expect all 3 lights to come out, cannot. Okay, so you have to put it to a secondary circuit and put a relay switch that can handle a much bigger voltage voltage supply lah. Okay, so the circuit that we want is circuit Y for all the 4 reasons stated above. Okay, right, let's move on to Penang. Oh no, sorry everybody, this is going to take us longer than usual because if we haven't hit SMK Agama kan means we're still a long way more. Okay, hang in there, hang in there. Okay, last class of the year. Okay, semiconductor diode, name the area labeled J. This area, when you have the P and N together and there's nothing in between, this is called the depletion region. Okay, the depletion region, just as a side note, the voltage that you require to close up the depletion region is called the junction voltage. Okay, it's called the junction voltage. This is just extra information lah. Okay, diagram 7.2 shows a circuit using a diode, okay, to light up the light bulb connected to a cathode ray oscilloscope. Diagram 7.3 shows the wave pattern. Okay, explain why the wave pattern is displayed on the CRO screen as shown above. Okay, so to help you to explain this, okay, remember this as the CNC method lah. Okay, talk about the connection and then the current flow. Is what kind of connection, what kind of current flow. Okay, CNC method. So in the first half over here, okay, so you're right, during the first half cycle. Okay, so the connection is, there are only 2 types of connection, forward bias, reverse bias. Since there is current, so it will be forward bias. Connection is forward bias and current is allowed to flow. Okay, and then the flat part is the second half. Okay, so then you write the same thing, connection and current. Okay, during the second half cycle. And there are only 2 half cycles because 2 halves okay, connection is reverse bias. and current current does not flow. Okay, so whenever you explain a rectification, especially half-wave rectification, okay, talk about the connection, talk about the current in every half cycle. Okay, the connection and current in every half cycle. There's only two half cycles. First half cycle, second half cycle. Okay, can I say, I have people ask this before. What if I write during the second half cycle is forward bias and current allowed to flow? During the first half cycle, current connection is reverse bias and current is not allowed to flow. Can lah, okay. Really nobody, it's a small matter lah. Okay, which is the first and which is the second. I think it's very inconsequential lah. Okay, really, I don't think it makes much of a difference. So don't worry about it. You can write it either way. Okay. All right, engineer wants to use an alternating current power generator. Okay, we see the same question again, the smartphone charger. This question had come out already actually last year or 2 years ago, smartphone charger. Okay, but we see it happen again. Uses a direct current. Sorry, I need to mention, the one that came out 2 years ago was from electromagnetism, not so much on electronics. Okay, so they may use the same thing, but this time they will ask electronics. Okay, based on this, the number of diodes used, definitely we want 4. Okay, this is normal. And the reason is to produce full wave rectification. Okay, standard answer lah. Okay, 4 diodes, full wave rectification. The type of wire, copper. Okay, copper or constant, but generally we will go with copper wire. I think this is a standard one. Okay, low resistivity or low resistance lah. Either one also can. Okay, I hope that by now you're used to the idea that, okay, as long as you say copper wire, low resistance, copper wire, low resistance, so that you know. Additional electronic components, I think if you've been following our discussion from the beginning, we always thought that the additional one is either diode or capacitor. Okay, the function of the capacitor is to smoothen the output current. Okay, to smoothen the output current. So this one, there's really not much variation over here, except that I like this question because of this one. Like it gives me a chance to talk about how to describe the half-wave rectification explanation. Okay, let's move on. At SBP. Okay, hang on. I think we got like a few more to go. Okay, SBP, yeah. So this is an essay question, okay? So state the function of the transistor with regards to this. Okay, with regards to this, if you have an LDR circuit, this is an automatic switch, not current amplifier. Okay, current amplifier, you want to have mic, speaker, those are current amplifier situations lah. Okay, automatic switch. Okay, does the LED light up at night? Okay, the most important thing is, if you remember from our explanation earlier, this one, at night the resistance is high, LDR. At night the resistance is high. So when we take a look at this, oh no, where am I? At night the resistance is high. Oh, it's this one. Okay, at night the resistance is high. If the resistance is high, the voltage is high, base current flows. Okay, so yes. Okay, yes is the answer, and then explain your answer. We go back to this one again. Okay, the starting point is at night the resistance of the LDR is high. If the resistance of the LDR is high, the base resistance is high, base voltage is high, base current flows, transistor switch on, collector current flows, and the end point is the LED lights up. Okay, so the starting point and the ending point is always the same. It's always different, but the rest in between is always the same. Okay, it's a good idea to memorize this flowchart because it makes our explanation very, very easy. I know it's long for a 4-mark question, but the flow is there and it's complete. Okay, cannot go wrong with this. All right. Calculate the potential difference. We've seen this question again and again, but let's try. Across the resistor and the LDR, which means the whole thing. Okay, there's no calculation over here. If you're provided 6 volts, this answer is 6 volts. Okay, potential difference across the resistor only. Let's take a look. Potential difference across the resistor only. So the question is, the LED will illuminate when the potential difference across the LDR is a minimum of 1 volt. Okay, I guess you have to assume that it's 1 volt lah. Okay, so if this is 1 volt, by logic, this will be 5 volts. Really nothing to think about here. Okay, 5 volts. Why is it 2 marks? I also don't know. Okay, the maximum resistance of the LDR for the LED to light up. So if you use our ratio method, okay, 5 volts is 10 kilo ohms. So 1 volt, logic will tell us that this is 2 kilo ohms. There's really nothing over here. Okay, 2 kilo ohms. Just use the ratio method. Okay, I hope this makes sense. 5 volts is 10 kilo ohms. 1 volt is... yeah. Okay, there you go. All right, let's move on. Fire alarm system circuit. Okay, we have the fire alarm situation again. Again, this is from page 68 in your black book. Okay, I think at this point you kind of know, I hope you know what to put here lah. Okay, AB should be a battery, I guess. Okay, connected in forward bias to the transistor. Okay, okay, the problem is now fire alarm. Fire alarm means you need a thermistor. Okay, and thermistor, we put it up here. So here should be the thermistor, and therefore down here should be a rheostat. A rheostat or resistor. No, sorry, resistor. Okay, a standard resistor lah. And then over here, since it is an alarm, so you want to have an alarm. Okay, so if you take a look, AB should be, the positive should be upwards, okay, because we want it to be forward bias. Okay, so either this or this, dry cell Y lah. Okay, CD is the alarm. Okay, so electric bell. Okay, EF should be the thermistor. Okay, not the LDR. Okay, and then finally is, at this point, you know that you are going for T already lah. Okay, the standard resistor. Okay, so the dry cell Y, why you would choose dry cell Y instead of dry cell X is to have a forward bias connection with transistor. Okay, the electric bell is what do we do just now for the alarm? Convert the electrical energy to sound energy. Okay, convert electrical energy to sound energy. Okay, and then the thermistor would be low resistance. I think this is the black book answer. Low resistance when the temperature is high. Hold on, let me check something. Yeah, low resistance when the temperature is high. Okay, and finally, okay, this one is the hard one lah. Not really hard lah. We have not discussed this before. So the reason why there is a separate resistor and it's a perintang tetap is a set resistor, okay, because its main function is to act as a potential. Oh man, you know what? Let me write this up here. Potential divider. Okay, the main function of the set resistor is to act as the potential divider. So it takes away some of the voltage supply. Okay, according to what happens with the thermistor lah. If the thermistor takes some, then the resistor will take the rest. Okay, so that would be the reason for this lah. Okay, dry cell Y, forward bias, electric bell convert electrical to sound. Technically electrical to kinetic to sound lah, because screen makan. Okay, thermistor low resistance when the temperature is high. This is a set answer. Okay, and the potential resistor as a potential divider also a set answer. Okay, so we're going for dry cell. Component set T. Okay, SMKA means once we hit SMKA means we're nearing the end already. And the good news is question 4 lah. Okay, so it's not an essay question. Okay, diagram 4.1 shows a simple cathode ray tube. Cathode emits electrons when switch P is closed. Wow, cathode ray tube again. Name the process that enables emission of electrons at the cathode. First time we're seeing this. In the past, it's always, what is the meaning of thermionic emission? Now they're asking you to name the process. The process is thermionic emission. Okay. When electrons flow in cathode ray tube, the current produced in 5 seconds is 0.01 ampere. Calculate the total charge. This is a formula given at the beginning of your question paper. Q equals to IT, okay, which is 0.01 times 5. Okay, 0.05 coulomb. Okay, this is the total charge of the electrons. This one, if you don't know, it's okay lah. I mean, it's not really from electronics. It's actually from electricity. But as I said just now, you cannot really run away from the other two chapters, chapter 3, 4, 5. There's a reason why they are in succession, because they're actually all connected. Okay? Electricity, electromagnetism, electronics. All right, 4.2 shows, oh wow, there's no English for this. Menunjukkan lintasan satu sinar cathode. Shows a path of a cathode ray that is incomplete. Okay, and in the electric field. So positive is here, so we know that up here will all be the positive, okay, and this will be negative lah. So complete the path of the cathode ray. Most important thing is that it goes to the positive. And I want you to notice this. Sorry, when I was looking at the marking scheme, I noticed that they are so fussy about this. It must touch, okay, it must touch the positive plate. Okay, you cannot draw like, yang penting dia ke atas lah, macam ni. Ini salah. Okay, so it is said lah, okay, in the marking scheme, it must touch the positive plate. Okay, for marking scheme purposes. Okay, whether it is a big angle or small angle, at this point we don't really care. The most important thing is it deflects towards the positive plate. Okay, give one reason, the main reason why the cathode ray go towards the positive plate. If you talk about cathode ray, is electrons are negatively charged. Okay, most important. It's the most important characteristic. Okay, potential difference. Once again, thermionic emission, blah, 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 blah. We are talking about the two formulas. EV equals to half mv squared. Okay, question is calculate the electrical potential energy. It means calculate EV only. Okay, electrical potential energy is EV. Okay, electrical potential energy lah. So this is 1.6 times 10 to the power negative 19 times with the voltage, of 550. So this will give us 8.8 times 10 negative 19. Unit for all energy, everybody, unit for all energy is joule. The only time where the unit for energy is slightly different is in electricity, which is kilowatt hour. Okay, this is electrical energy. Okay, and this one we use kilowatt hour is just to calculate cost only. The only time where we calculate energy in a different unit, okay, is to calculate the cost of the electricity, and that one we use kilowatt hour. Selain daripada itu, make sure that you put the unit for energy as joule. Oh well, I think there's another instance, but I cannot remember it now. Okay, now by using the formula half MV equals to EV, you've already calculated EV, so don't waste time. 8.8 times 10 to the power negative 19 equals to half. Mass is given, right? Yeah, 9.11 times 10 to the power of negative 31. Okay, times V squared. Don't forget to square root the V. Okay, you will get the answer. V equals to 1.39 times 10 to the power of 7 meters per second. Okay, so it's a fairly simple formula, I think. It's a fairly simple formula, but remember that actually this formula consists of two components that can be calculated separately if you need to. Just like the impulse formula. Impulse is Ft equals to mv minus mu. Bahkan each of this is actually one way to calculate the impulse. Okay, so it's not really a formula, but it's just a relationship between the two different methods of calculating the impulse. All right, final question. Okay, I'm so glad that this is not an essay question because I'm actually running out of breath, running out of voice already lah. Okay, Terengganu, question number 5. Okay, final question for the final class for the year. Yay. Terengganu 2023, diagram 5.1, 5.2 shows two identical circuits, okay, that are in two states. Oh, wow. Dark and bright. Okay. What is the type of transistor used? Take a look at the arrow. It's pointing downwards, so it will be NPN transistor. Okay. Compare the base voltage. If you take a look at this deflection and take a look at this deflection, it's quite obvious that 5.2 is bigger than 5.1. Okay. The lighting of the bulb. Okay, lighting of the bulb is not bigger, smaller. You have to say which one lights up and which one doesn't light up. Okay, so 5.1 lights up and 5.2 doesn't light up. Okay, 5.1. Sorry, did I say 5.1? Okay, 5.1 doesn't light up. 5.2 lights up. Okay, it's a slightly different compare question lah. Okay, so learn to be flexible lah. Okay, base current. Well, if the bulb doesn't light up, means the transistor is off. If the transistor is off, means the base current doesn't flow lah. Okay, so base current in this case, you cannot say one is bigger than the other because one got base current, one no base current. So you cannot say one is bigger than the other. So you use the same thing as the bulb just now. Okay, no base current in 5.1. Okay, base current flows in 5.2. Okay, slightly different compare method. Slightly different compare method. If you notice just now, okay, actually, if you notice in this question, the LDR is at the top. Sorry, at the top. Okay, that's why when it is dark, there is no light. It's a very strange LDR. This is a strange circuit lah. Kalau kita mau keadaan gelap dan mentol menyala, bahkan the LDR should be at the bottom. Okay, but in this case, this question, the LDR is on top. It's not a mistake in the question. I'm sure they purposely put it that way. Okay, but just for us to remember that if you want the bulb to light up at night, the LDR must be at the bottom because the resistance of the LDR is high at night. Okay, so what is the relationship between the base voltage and the base current? Okay, so this one, again, this is kind of a weird relationship because base current, in this case, base current is either flow or no flow. Okay, so you have to write when the base voltage is high. Remember our transistor flow chart. Base voltage high, base current flows. You cannot say base current is high. Well, I guess you can say it's high lah, relatively lah. Okay, it's relatively high, but we follow the pattern of our this one. Okay, base voltage high, base current flows. That is the order lah. Base current 5.1 less than 5.2. Oh, you want to write it as base current 5.1 is less than 5.2. Sure. 5.1 is less than 5.2. I think in either case, both answers can be accepted lah. Okay, you write no base current in 5.1, base current flows in 5.2, or you can write 5.1 is less than 5.2. But if you're going to say that, then I'm going to have to give a slightly alternative answer. Okay, 5.1 is less than 5.2. If your answer is in green, then your answer over here will be when the, oh no, then you can say the bigger the base voltage, the bigger the base current. Okay, so I think this is a conditional answer lah. If you answer in green in number 3, you must answer in green in the next question. If you answer in red, then you answer in red. I think that will be how the marking scheme will work. Okay, I don't think your logic is wrong lah. Okay, the fact that there is base current but it's not big enough for the transistor to flow can. But make sure that when you answer the base voltage with the base current in C1, you answer the green color one because you're already talking about the comparison there. Bigger the base voltage, the bigger the base current. Okay, base current with the collector current. This one is definitely either way lah. Okay, bigger base current. Okay, bigger collector current. I think that's it lah. Okay, transistor switch on, bigger base current, bigger collector current. Okay, 5.3 shows a transistor circuit that consists of a light-dependent resistor, LDR. I'm so sorry, everybody. Just give me like 5 more minutes. Almost done. Okay, when LDR is detected, sorry, there's a missing word over here. When the LDR detects light. Okay, when the LDR detects light, the potential difference of LDR is 1.2 volts. You kind of know where this question is going. Okay, calculate the resistance of the LDR. I think we've done this so many times that I hope that you know lah. Okay, if this is 6 volts, this is 1.2. That means this one will be 4.8. Okay, 4.8 volts minus 6 minus 1.2 is 4.8. So the question is this: 4.8 volts equals to 10 kilo ohms. Okay, so 1.2 volts apa macam? Okay, apa macam? Okay, so I'm not going to give you I'm not going to give you the working for this, but I want you to figure out this answer for yourself. Okay, I want to figure this answer because it's not difficult. Okay, it's not difficult, you just need to work your way through it. Okay, the answer is 2.5 kilo ohms. Okay, but I want you to figure out how this is done. Okay, it's only a 3-mark question lah. I don't think really that much is. If you follow the ratio, 2.5 is the logical answer. Okay, all right. Thanks everybody for being faithful to the end. So I hope that these 5 sessions has been helpful. Just as a reminder, okay, for those of you who are in All Saints, when we go back to school, okay, you don't have to bring these 5 papers anymore, unless you want to study it lah. Okay, but the first thing that we're going to do is we're going to go through the Ramalan set. Okay, the 2 Ramalan papers are the first things that we're going to go through. And then only we're going to go through the electricity paper and what's the other chapter? I can't remember. Okay, the other 2 papers lah. Okay, if I need to, waves, thank you. Electricity and waves. I think we'll do waves first there, and then electricity lah. Okay, and most likely, if we have time, if we have finished all the 4 handouts that are after this, then I will do quantum physics with you one last time, as in a session like this lah. Okay, it may be that I may have another Google Meet to kind of finish everything. Okay, my intention is to finish at least to make sure that I think quantum physics also I need to cover, because something tells me that quantum physics will be heavy this year lah. I don't know why. Okay, maybe it's just my luck lah, but I think that I need to cover quantum physics to make sure that we are on track. Okay, but I think the 5 chapters that we have covered is enough to get you through, to prepare you for the paper. Okay, as we go nearer and nearer, we will discuss even more lah. Okay, so if there's anything, okay, don't hesitate to message me and ask. Otherwise, Happy New Year. Okay, Happy New Year to everybody. Okay, I will see you in the coming year. Okay, bye.